For most of human history, planets were thought to wander freely, small lights drifting across the sky, each moving to its own rhythm. But when motion was measured carefully, something unexpected appeared. Almost every planet turns the same way, not randomly, not independently. Across vast distances and very different worlds, a shared direction quietly persists. Tonight's journey is not about coincidence, it is about origin. About how spinning worlds remember the moment they were born. Welcome to the Sleepy Scientist. Let's begin. Almost every planet in the solar system rotates in the same general direction. This is not something that announces itself loudly. There is no cosmic arrow painted across the sky, no obvious sign that worlds are quietly agreeing on how to turn. The pattern only reveals itself when motion is watched patiently, over long stretches of time with careful attention to detail. From Earth, planets appear calm and distant. They drift slowly against the fixed background of stars, changing position night after night, year after year. Early astronomers focused on these wandering paths, trying to understand why planets looped, slowed, or even appeared to move backward for a time. Rotation was far more subtle. A planet's spin is inward, quiet, revealed only through shadows, surface markings, and the faint clues left by changing light. But once those clues were gathered, something remarkable became clear. Mercury rotates slowly, taking many weeks to complete a single turn. Jupiter spins so quickly that its day lasts less than half an Earth day. Saturn flattens at its middle because of its speed. Mars turns at a familiar pace, giving it days not so different from those on Earth. The speeds vary widely. The sizes could not be more different. The compositions range from rocky worlds to vast spheres of gas. And yet, almost all of them turn the same way. Viewed from above the north side of the solar system, the planets rotate in an anti-clockwise direction. This is true for Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Even Mercury, slow and strange in many ways, follows the same basic sense of spin. The differences lie in how fast they turn, not in the direction they choose. That shared motion is the first quiet clue that these planets did not form independently. Astronomers determine a planet's rotation in several gentle, indirect ways. For worlds with visible surfaces, rotation can be tracked by watching surface features drift across the planet's face. Dark regions, bright patches, storms, and ice caps all move predictably as the planet turns. Mars reveals its spin through changing polar caps. Jupiter's rotation is traced by its cloud bands and its famous long-lived storm. Saturn's subtle stripes and shadows offer similar hints. For planets wrapped in thick clouds, the task becomes more delicate. Venus hides its surface completely beneath a dense atmosphere, but radar observations allow astronomers to bounce signals off the ground below, revealing how the planet slowly turns beneath its cloud cover. In that case, the measurements revealed a surprise. Venus rotates in the opposite direction and very slowly, taking longer to turn once than it does to orbit the Sun. It is an exception that stands out clearly precisely because the rest of the system is so consistent. For the outer planets, rotation can also be inferred through magnetic fields. As a planet spins, its magnetic field rotates with it, sweeping past spacecraft and detectors. These repeating signals act like a steady heartbeat, marking each rotation with quiet regularity. Even when clouds shift or storms evolve, the magnetic rhythm remains. When all of these measurements are placed side by side, the pattern becomes impossible to ignore. The solar system does not behave like a collection of unrelated objects. It behaves like a family. The planets orbit the Sun in nearly the same plane, moving in the same orbital direction. Their moons often orbit in that same sense as well, and almost all of the planets rotate in agreement with that larger motion. This alignment is not perfect, but it is far too consistent to be random. If planets formed independently, scattered through space and later captured by the Sun, their spins would be expected to point in all directions. Some would rotate clockwise, others anti-clockwise, many tilted at extreme angles. There would be no clear preference, no dominant pattern. Chaos would rule. That is not what is observed. Instead, the solar system shows a strong memory of its earliest moments. Rotation appears not as an afterthought, but as something inherited, passed down quietly from one stage of formation to the next. The shared spin is not imposed. It is carried forward. Even the variations tell part of the same story. Uranus, famously tilted on its side, still rotates in the same directional sense when viewed from its own north. Its orientation is unusual, but its underlying spin still fits within the broader pattern. Neptune, distant and cold, follows along as well. Jupiter's immense mass does not break the rule. Saturn's rings, spread wide and thin, orbit in harmony with the planet's spin. The exceptions, like Venus, stand out precisely because they are rare. When astronomers map rotation across the solar system, they do not see disorder. They see a system that began with a shared motion and never fully let go of it. Differences accumulate, impacts happen, axes tilt, speeds change, but the overall direction remains stubbornly consistent. This consistency tells a deeper story than speed ever could. Speed can be altered easily. A collision can slow a planet down or speed it up. A moon can tug on its parent world, gradually reshaping its rotation over immense spans of time. Atmospheres can apply subtle braking forces. All of these processes can change how fast a planet turns. Changing direction is much harder. To reverse a planet's spin entirely requires extraordinary circumstances. It demands either a massive, precisely angled collision or a long history of powerful tidal interactions. These events are possible, but they are not common. The fact that most planets avoided such reversals suggests that their original motion was strong, coherent, and deeply rooted in the system's earlier structure. There is something quietly comforting about this. In a universe that often feels violent and unpredictable, the solar system reveals a surprising calm, not because nothing dramatic happened, but because even drama unfolded within boundaries set early on. Planets may wander slightly, they may wobble, they may wear scars from ancient impacts, but beneath all of that they continue to turn together, keeping time with a motion older than the planets themselves. This shared spin is not a rule written into space by necessity. Other solar systems may spin the opposite way entirely. If viewed from their own north, their planets might turn clockwise instead. Direction itself is not special. What matters is agreement. The solar system chose a direction long ago, and nearly every planet has followed it ever since. That agreement is the starting point for understanding how planets form, how disks of gas behave, and how order can quietly emerge from vast, drifting clouds of matter. It is not a loud clue. It does not sparkle or explode. It simply turns steadily and reliably together. The phrase anti-clockwise sounds precise, almost absolute, but in space it is anything but. Direction depends entirely on where the observer is standing, or in this case, floating. There is no universal up or down written into the universe, no built-in left or right. Space does not come with arrows or labels, it simply exists, and direction is something added by perspective. When astronomers say that planets rotate anti-clockwise, They are quietly making an agreement about viewpoint. They are choosing to look at the solar system from a particular angle and describing motion from there. Without that shared reference, the description would lose its meaning. To understand this, it helps to imagine the solar system not from Earth's surface, but from far above it. Picture the Sun at the center with the planets spread out around it in a broad flattened disk. This disk has two sides. One can be called North, the other South, but those names are conventions, not cosmic truths. Astronomers define the north side of the solar system based on the direction of Earth's orbit and the tilt of Earth's axis. From that chosen side, most planets move around the Sun anti-clockwise, and most of them rotate anti-clockwise as well. If the entire scene were viewed from below the disk instead, everything would appear reversed. Orbits that looked anti-clockwise from above would now look clockwise. Rotations would flip too. Nothing physical would have changed, only the description would be different. This is where confusion often creeps in. It is tempting to think of anti-clockwise as a property of the planets themselves, as if they are somehow choosing a special direction that exists independently of observation. In reality, the planets are simply spinning. The labels are human conveniences layered on top of that motion. This does not make the pattern any less real. What matters is not the word anti-clockwise, but the shared sense of rotation. The planets agree with one another. They turn in the same direction relative to the plane of the solar system. That agreement remains true no matter which side of the disk is chosen as the viewing point. The idea of reference frames helps make this clearer. A reference frame is simply a chosen point of view from which motion is described. On Earth, this happens constantly without much thought. Standing on the ground, it feels natural to say that the sun rises in the east and sets in the west. From a broader perspective, Earth is rotating, and the sun is not rising at all. Both descriptions work within their chosen frames. In space, reference frames become even more important. A spinning planet does not carry a tag that says clockwise or anti-clockwise. It simply rotates around an axis. Whether that rotation appears one way or the other depends on the observer's position relative to that axis. Move to the opposite side and the apparent direction flips instantly. This is why astronomers always specify the viewpoint, even if only implicitly. When discussing the solar system, the agreed reference frame is usually one that looks down on the plane of the planets from the north side. Within that frame, the shared rotational direction becomes obvious and consistent. Without that agreement, conversations about direction would quickly become tangled. This perspective dependence also explains why some descriptions can sound contradictory at first. For example, Earth rotates from west to east. This is often stated as a simple fact. But that description assumes a viewer standing on Earth's surface, using the familiar directions of a map. From above the North Pole, that same motion is described as anti-clockwise. From above the South Pole, it becomes clockwise. All three statements describe the same physical motion. None of them are wrong. They simply belong to different frames of reference. Planets behave the same way. Mars rotates from west to east when described in surface directions. From above the solar system's north side, it rotates anti-clockwise. From the opposite side, it rotates clockwise. The underlying motion has not changed, only the language has. This can feel unintuitive because everyday experience rarely requires switching frames so freely. On Earth, directions feel fixed. Up stays up, north stays north. But even here, those ideas are conventions tied to gravity, geography, and habit. In deep space, those anchors disappear. There is also a subtle difference between rotation and orbit that sometimes adds to the confusion. Rotation refers to a planet spinning around its own axis. Orbit refers to a planet moving around another object, such as the Sun. In the solar system, both motions share the same general directional sense when viewed from the agreed reference frame. The planets orbit the Sun anti-clockwise, and most of them rotate anti-clockwise as well. This shared alignment is the important point. It would be possible for a planet to orbit one way and rotate the opposite way. Venus does exactly that. It moves around the Sun in the same orbital direction as the other planets, but its rotation is reversed. This makes Venus stand out, not because clockwise or anti-clockwise is special, but because it breaks the shared agreement seen elsewhere. Without a clear understanding of perspective, Venus can seem more mysterious than it needs to be. It is often described as rotating backwards, but backwards relative to what? The answer is always relative to the chosen frame. Venus simply spins in the opposite sense compared to most other planets in the same system. This is not a moral failing. It is a historical outcome. Another common misunderstanding is the idea that anti-clockwise has something to do with north, being up on a page or screen. Maps often place north at the top, but this is a design choice, not a law of nature. Space does not care about page orientation. The solar system could be drawn rotated 90 degrees, or upside down, and the physics would remain unchanged. What remains consistent is the relationship between the planets themselves. They share a plane, they share an orbital direction, and most of them share a rotational direction relative to that plane. That relationship is the real signal, not the words used to describe it. Once this is understood, discussions about planetary rotation become much calmer. The emphasis shifts away from labels and towards structure. The question stops being why anti-clockwise and becomes why shared. Why do so many planets agree on how to turn, regardless of which words are used to describe that turning? By gently setting aside the idea of absolute direction, the solar system becomes easier to understand, not harder. Motion becomes something relational rather than fixed. Patterns become clearer. Exceptions stand out more honestly. Anti-clockwise is not a rule of the universe. It is a description chosen carefully to help reveal a deeper consistency beneath the motion of worlds. And once that consistency is seen, the choice of words fades into the background, leaving only the quiet agreement that has been there all along. At first glance, the solar system appears three-dimensional and untidy. Planets circle the Sun at different distances, some close and fast, others slow and remote. Their paths stretch across enormous spans of space, unfolding over years, decades, and centuries. From within it, the system feels spacious and complex, with no obvious sense of order or structure tying everything together. But when the solar system is viewed from a distance, a quieter pattern becomes clear. Almost all of the planets orbit the Sun within a remarkably thin, flattened region of space. Their paths do not scatter wildly above and below one another. Instead, they trace out gentle, nearly circular tracks that sit close to a shared plane, like grooves pressed into a vast disk. Compared to the overall size of the solar system, this plane is strikingly narrow. This flatness is not subtle once it is noticed. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit within a few degrees of the same plane. There are small tilts and slight deviations, but nothing that resembles randomness. Even the asteroid belt follows this same broad arrangement, with countless rocky fragments moving within the same flattened region around the Sun. This shared orbital plane is one of the most important clues to how the solar system formed. If the planets had formed independently, or if they had been captured one by one from different regions of space, their orbits would point in many directions. Some would loop far above the Sun's equator, others far below it. Over time, the system would resemble a loose swarm rather than an orderly disk. That is not what is observed. Instead, the planets move as though they were gently laid out on a single surface, each tracing its own path while agreeing on where that surface lies. This agreement hints strongly at a shared beginning, shaped by motion long before planets existed. Flat systems do not arise by chance. They are a natural consequence of rotation. When a cloud of gas and dust begins to collapse under its own gravity, it almost never does so in complete stillness. Even a tiny amount of initial motion, barely noticeable at first, becomes increasingly important as the cloud shrinks. As material falls inward, that faint motion speeds up, and the cloud begins to rotate. As rotation strengthens, something subtle but powerful happens. Motion perpendicular to the axis of rotation becomes harder to sustain. Particles moving above or below the developing plane collide, interact, and exchange energy. Over time, these vertical motions are reduced, leaving most of the material confined to a flattened disk. This behavior is not unique to space. It appears in many rotating systems. Water swirling toward a drain spreads into a thin sheet before disappearing. Spinning dough flattens as it stretches outward. Saturn's rings exist as a disk rather than a sphere for the same reason, shaped by rotation and countless gentle interactions. The solar system followed this same logic. The shared orbital plane tells us that the planets formed within a rotating disk of gas and dust. That disk established a preferred plane early on, and once it did, it guided everything that followed. Planets grew within it. Smaller disks formed around those planets, giving rise to moons. The structure repeated itself at different scales, each shaped by the same underlying motion. This flatness connects directly to the shared direction of planetary rotation. When planets form inside a rotating disk, their orbits naturally align with the disk's motion. They move around the Sun in the same direction that the disk itself is turning. But something more subtle happens as well. The material that falls onto a growing planet carries the disk's motion with it. That material does not arrive evenly from all directions. It comes primarily from within the plane of the disk, already moving in a preferred direction. As a result, planets tend to inherit not only the plane of motion, but the direction of motion too. The flatness of the solar system and the shared spin of its planets are not separate mysteries. They are two expressions of the same formative process. Orbital alignment provides the foundation upon which rotational agreement is built. Without a shared plane, there would be no reason for planets to rotate coherently. Each world would form from material arriving at random angles, spinning however chance allowed. Instead, the disk quietly shaped every growing world. Even the small deviations fit naturally into this picture. No disk is perfectly flat. Gravitational interactions, lingering turbulence, and distant encounters can introduce slight tilts over time. Planets can gently nudge one another across billions of years. These effects add texture rather than chaos, leaving the overall structure intact. The solar system's flatness also explains why eclipses and planetary transits are possible, and why alignments occasionally grace the night sky. These events rely on the fact that the planets move within the same broad sheet of space. Without that shared plane, such moments would be rare or impossible. There is a quiet elegance in this arrangement. The solar system did not need to be flat. Space places no requirement on such order. Gravity could have assembled something far messier, but rotation gradually smoothed away excess motion, leaving behind a calm geometry that persisted. Once established, That geometry became a kind of memory. Every orbit traced today follows a path laid down during the system's earliest moments. Every shared direction of motion reflects the same ancient rotation. The planets differ wildly in size, composition, and appearance, yet they remain united by this inherited structure. In this way, flatness is not a limitation. It is a record, preserving the story of a time when the solar system was not a collection of the worlds, but a single drifting cloud, slowly turning long before planets had names at all. Long before the sun shone, before planets traced their paths or days had any meaning at all, the solar system existed in a much quieter form. There was no central star, no distinct worlds, no clear boundaries. Instead, there was a vast cloud of gas and dust drifting through space. It was cold, diffuse, and unremarkable, one of countless such clouds scattered across the galaxy. From the outside, there was nothing about it that suggested it would one day become a system of planets, let alone one with such a clear sense of order. This cloud was mostly hydrogen and helium, the simplest and most abundant elements in the universe, mixed with tiny grains of heavier material forged in earlier generations of stars. These dust grains were sparse, floating far apart, yet they played an important role. They gave the cloud texture, they allowed heat to radiate away, they helped the cloud respond to gravity more effectively. For a long time, nothing dramatic happened. The cloud drifted gently, shaped by faint gravitational pulls, distant shock waves from exploding stars, and the slow tides of the galaxy itself. Inside it, particles moved in all directions, colliding softly, exchanging energy, wandering without purpose. There was no sharp boundary between the cloud and the space around it. It simply faded into the background of the galaxy. Then gradually gravity began to matter more. Perhaps a nearby supernova sent a ripple through the cloud. Perhaps it passed through a denser region of the galaxy. Perhaps its own slow cooling allowed gravity to gain the upper hand. The exact trigger is not fully known, and it does not need to be dramatic. What matters is that once gravity began to dominate, the cloud started to change. Material began to drift inward. This inward motion was not uniform or perfectly symmetrical. No natural system ever is. Some regions were slightly denser than others. Some particles were moving a little faster. Some directions offered less resistance. As gravity pulled everything closer together, these small differences became more important. And this is where spin enters the story. The cloud did not begin with no motion at all. That would be extraordinarily unlikely. Even the emptiest regions of space contained subtle flows, tiny currents, and gentle rotations inherited from larger structures. The pre-solar cloud already carried a faint sense of movement, a barely noticeable overall twist. At first, that motion was insignificant. The cloud was enormous, and the rotation was spread thinly across a vast volume. But as gravity caused the cloud to contract, that same amount of motion was squeezed into a smaller and smaller region. As the cloud shrank, its rotation naturally sped up. This is not because any new force was added, or because something reached in from outside and spun it like a wheel. It happened because motion has a tendency to persist. Once something is moving, it resists stopping. When the size of a rotating system decreases, the rotation becomes more noticeable, simply because there is less space over which to spread it. This process is quiet and unavoidable. A slowly turning cloud does not need encouragement to spin faster as it collapses. It does not need guidance or fine-tuning. The increase in rotation is a direct consequence of shrinking while conserving motion. As gravity pulls matter inward, rotation emerges naturally, not as a special feature, but as an inevitable outcome. As the pre-solar cloud continued to contract, its rotation became clearer. What was once an almost imperceptible drift turned into a gentle, steady spin. The cloud was still enormous, still cold, still lacking a central star, but its future shape was already being decided. Rotation began to shape the collapse. Material falling inward did not move straight toward the center. Instead, it followed curved paths, influenced by the cloud's growing spin. Particles approaching from different directions interacted, collided, and gradually settled into patterns that favored motion around the center rather than directly into it. Over time, this led to a subtle but important change. The collapsing cloud began to flatten. Material moving in the direction of the rotation found it easier to remain in orbit around the growing center. Material moving strongly above or below the developing plane collided more often, losing energy and settling closer to that plane. Slowly, almost imperceptibly, the cloud transformed from a loose three-dimensional shape into something flatter and more organized. All of this happened without intention. There was no moment when the cloud decided to become a disk, no boundary where chaos suddenly gave way to order. This structure emerged gradually, guided by gravity and motion working together over immense spans of time. At the center of this spinning, flattening cloud, density increased. More and more material gathered into a growing core. Temperatures rose as particles collided more frequently. Pressure built. Eventually, conditions became right for the birth of a star. But even before the sun truly ignited, the system already had a direction. The rotation of the cloud defined a sense of orientation that everything else would inherit. The disk that formed around the central region carried that rotation forward. The material within it moved together, sharing the same general sense of spin. This was not imposed later. It was present from the very beginning. What is striking about this process is how little it depends on special circumstances. The cloud did not need to be perfectly shaped. It did not need to rotate quickly at first. It did not need to experience a violent trigger. Any small initial motion, combined with gravity and time, would have led to the same general outcome. Rotation in this context is not an extra feature added to the system. It is a natural consequence of collapse. This is why spinning disks are so common in space. Stars form with disks around them. Planets form within those disks. Galaxies themselves often take on flattened, rotating shapes. The same basic physics applies across an enormous range of sizes. The pre-solar cloud was simply following a pattern written into the behavior of matter and motion. As collapse continued, the disk became more pronounced. Material within it moved in orderly paths circling the growing sun-to-be. The sense of direction became clearer. The flatness became more defined. The stage was set for planets to form. By the time individual worlds began to emerge, the system's overall rotation was already well established. The planets did not choose a direction. They inherited one. Their shared spin is a direct echo of that earliest motion, preserved through billions of years of change. In this way, the story of planetary rotation begins not with planets at all, but with a drifting cloud slowly gathering itself, quietly turning as it did so. There was no forceful push, no deliberate spin, only gravity, motion and time working together in the simplest way possible. And once that motion existed, it never truly went away. Spin has a remarkable persistence. Once motion begins, it does not like to disappear. It can change shape, shift speed, or spread itself out, but it resists being erased entirely. This quiet stubbornness is one of the most reliable behaviors in nature, and it plays a central role in explaining why planets continue to rotate in the way they do. The idea behind this persistence is often called angular momentum. but the name itself is less important than the behavior it describes. At its heart, it is simply the tendency of rotating motion to be conserved. When something is spinning, that spinning wants to continue unless something actively interferes with it. This is not an abstract rule invented by physicists. It is something experienced in everyday life, even if it is rarely noticed. A slowly turning playground carousel will keep rotating for a long time if nothing touches it. A figure skater spinning on ice will continue to turn smoothly until friction with the air or the ice gradually slows them down. In space, where friction is minimal and distances are vast, this tendency becomes even more pronounced. The pre-solar cloud that gave rise to the solar system already carried a small amount of rotation. That motion did not vanish as the cloud collapsed. Instead, it was preserved, carried inward, and reshaped as the system evolved. Gravity pulled material closer together, but it did not cancel the motion that was already present. This is the key idea. Motion is not easily destroyed. It must be transferred, spread out, or redirected, but it does not simply fade away on its own. In a collapsing cloud of gas and dust, there is nothing efficiently draining away rotational motion. As a result, whatever spin exists early on becomes an enduring feature. As the cloud shrinks, something counterintuitive happens. The rotation speeds up. This is not because gravity actively twists the cloud faster, or because an external force reaches in and accelerates it. Instead, the increase in speed comes from the same motion being confined to a smaller space. An everyday analogy helps make this clear. When a skater pulls their arms closer to their body while spinning, they rotate faster. Nothing magical has happened. No new spin was added. The same rotational motion is now concentrated nearer to the center, making the turning more rapid. The collapsing cloud behaves in much the same way. Early on, the cloud was enormous. Its rotation was spread thinly across a vast volume. As gravity caused the cloud to contract, that same rotation became more noticeable. The system had less room to distribute its motion, so the spinning grew stronger. This relationship between size and spin is deeply reliable. Shrinking systems spin faster because the motion they already possess has nowhere else to go. Importantly, this does not require precision or balance. The cloud does not need to collapse evenly. It does not need to be perfectly round. It only needs to shrink while retaining its motion, and gravity ensures that both conditions are met. As the pre-solar cloud continued to contract, angular momentum shaped its behavior at every stage. Material falling inward followed curved paths rather than straight lines. Collisions between particles redistributed energy, but the overall rotation remained. The developing disk around the young sun carried the same sense of spin as the original cloud. Even when matter clumped together to form planets, this persistence continued. As planets grew, they accumulated material that was already moving within the disk. Each grain of dust and each fragment of rock carried a tiny contribution of rotational motion. When added together over millions of years, these contributions built up into a clear, measurable spin. This is why planetary rotation feels inherited rather than imposed. The planets did not need to be spun up later. They did not require a special event to set them turning. Their rotation emerged naturally as a result of growth within a spinning environment. The motion was already there, waiting to be gathered. Once a planet had acquired a certain amount of spin, that motion became remarkably difficult to erase. To significantly alter a planet's rotation requires either sustained interaction over immense periods of time or a dramatic, well-aimed collision. Small impacts tend to average out, nudging the planet slightly, but rarely overturning its overall direction. Tidal forces can slow rotation, but even these act gradually, taking billions of years to make major changes. This is why the direction of spin is so stable across the solar system. Speed can change, axes can tilt, days can lengthen or shorten, but the fundamental sense of rotation tends to persist because it is rooted in the system's earliest motion and protected by the conservation of spin. Even exceptions follow the same logic. Venus, for example, rotates in the opposite direction to most planets. This is not because it ignored the rules of angular momentum, but because its history likely included extreme interactions that altered how that conserved motion was expressed. The underlying principle still applies. The spin was not forgotten, it was transformed. Uranus, with its dramatic tilt, offers another example. Its unusual orientation suggests a violent past, perhaps involving massive impacts. Yet beneath that tilt, its rotation still carries the imprint of the original disk. The motion survived, even as the planet's posture changed. What emerges from all of this is a picture of remarkable continuity. From a drifting cloud to a spinning disk, from a growing star to orbiting planets, the same rotational story is carried forward. Angular momentum acts like a memory embedded in motion itself, preserving information about the past long after the original structure has changed. This memory does not fade easily. It is passed along quietly, reshaped but not erased. In the vacuum of space, where friction is scarce and time is abundant, this persistence becomes one of the dominant organizing principles. Systems evolve, but they do so while respecting the motion they already have. Spin is not added casually, and it is not removed lightly. This is why the solar system feels coherent. The planets rotate in a shared direction because they inherited a shared motion. That motion was strengthened as the system shrank, gathered as worlds grew, and preserved as those worlds matured. It was never forgotten, because nothing ever truly asked it to leave. In this way, spin is not a detail layered onto planetary formation. It is a foundational feature, woven into the process from the very beginning. Once motion begins, it tends to remember itself, and in the vast calm of space, that memory can last for billions of years. As the collapsing cloud continued to shrink, its future became clearer. The growing rotation did not remain evenly spread throughout the cloud. Gravity pulled material inward, but rotation resisted a straight fall toward the center. The result was a compromise. Matter moved closer, but it did so while circling, gradually arranging itself into a broad spinning disk surrounding a denser core. At the heart of that disk, the sun began to form. Material near the center grew increasingly compressed. Collisions became more frequent. Temperatures rose steadily as particles packed closer together. Eventually, the central region became dense and hot enough to mark the birth of a young star. But even as the sun ignited, it did not consume all the surrounding material. Much of the cloud remained spread out in a rotating disk that encircled the newborn star. This disk was not a thin, delicate structure at first. It was thick, turbulent, and full of motion. Gas and dust swirled in overlapping paths, colliding, sticking, and separating again. Yet beneath this apparent complexity, the disk shared a simple and important feature. Everything within it was moving in roughly the same direction. The sun formed inside this rotating environment, not separate from it. This arrangement explains something fundamental about planetary systems. Stars do not usually form alone, they form with disks. Wherever gravity gathers rotating material into a central object, a disk is a natural companion. The same balance between inward pull and sideways motion appears again and again throughout the universe. Disks are common because they are efficient. When matter collapses while rotating, it cannot fall straight inward without shedding motion. Instead of stopping, that motion redirects material into orbit. Over time, repeated interactions flatten the system, guiding matter into a disk where rotation and gravity coexist peacefully. This configuration allows material to remain close to the star without immediately plunging into it. That balance is remarkably stable. In a disk, particles can collide gently, exchange energy, and slowly evolve without disrupting the overall structure. Motion becomes organized rather than chaotic. Paths become predictable. Over long periods, this stability allows complex processes to unfold, including the growth of planets. This is why disks appear so often in space. Young stars are frequently observed with glowing disks of gas and dust around them. These disks can stretch for billions of kilometers, shining faintly as they reflect and emit light. Telescopes have captured images of such disks in various stages of development, some smooth and continuous, others carved into rings and gaps by emerging planets. The same pattern appears on much larger scales as well. Galaxies often take the form of vast rotating disks, flattened by rotation and shaped by gravity over billions of years. Saturn's rings follow the same principle on a smaller scale. Wherever rotation and gravity interact over time, disks tend to emerge. The disk around the young Sun was no exception. Within this disk, the direction of motion became firmly established. All material shared the same general sense of rotation, inherited directly from the original cloud. There was no ambiguity about which way was forward. The disk turned as a coherent whole, carrying gas, dust, and growing clumps of matter along with it. This shared direction mattered enormously. As material orbited the Sun, it followed paths defined by the disk's rotation. Collisions between particles tended to smooth out differences rather than amplify them. Objects moving against the dominant flow were more likely to collide and lose energy, gradually aligning their motion with the disk. Over time, the system became increasingly orderly. The disk acted like a guide, quietly encouraging agreement. This process did not require forceful correction or dramatic intervention. It happened naturally, through countless small interactions. Dust grains brushed past one another, gas swirled and mixed. Energy was exchanged gently but persistently. The result was a system in which shared motion became the norm rather than the exception. As the Sun continued to grow, its gravity strengthened. It cleared material from the innermost regions of the disk, drawing gas inward and shaping the surrounding environment. Yet the disk persisted, extending far beyond the young star, providing the raw material for planets yet to come. Importantly, the Sun's own rotation aligned with the disk. The same motion that shaped the disk also influenced the star forming at its center. As material fell inward, it transferred angular momentum to the growing Sun, causing it to spin. The star and the disk rotated together, reinforcing the system's shared sense of direction. This alignment is not perfect in every system, but it is common. It reflects the deep connection between stars and the disks that give rise to planets. They are not separate creations. They are different expressions of the same collapsing, rotating cloud. Within the disk, regions of higher density began to appear. Dust grains collided and stuck together, forming larger clumps. These clumps swept up more material as they orbited, gradually growing into solid bodies. Throughout this process, the disk's rotation continued to shape how material arrived. Incoming matter tended to add spin in the same direction rather than cancel it out. This is how shared rotation becomes locked in. Once the disk's direction was established, it became difficult for anything within it to ignore that motion. Growing objects naturally aligned their orbits and spins with the surrounding flow. The disk did not force agreement. It simply made agreement the easiest outcome. Over time, the disk thinned and cooled. Gas gradually dissipated, either falling into the sun or being blown away by stellar winds. What remained were the solid building blocks of planets, still moving within the same flattened structure and still sharing the same sense of direction. By the time planets fully formed, the system's rotational character was already deeply set. The sun shone at the center, spinning calmly. The planets traced their orbits within the disk's plane. Their rotations reflected the motion of the material from which they grew. What began as a faint twist in a drifting cloud had become an organizing principle for an entire planetary system. This sequence is neither rare nor fragile. Across the galaxy, young stars repeat the same pattern. Disks form, stars ignite, planets emerge, shared motion persists. The details differ from system to system, but the underlying process remains strikingly consistent. The birth of the spinning disk is the moment when direction stops being ambiguous and starts becoming history. From that point on, the system remembers how it turned. Everything that followed, from the spin of planets to the arrangement of moons, carried the imprint of that early rotation, not because it was imposed later, but because it was present from the very beginning. The disk did not merely surround the sun, it defined the future. Planets are not born all at once, they grow. Inside the spinning disk surrounding the young sun, matter did not suddenly assemble into fully formed worlds. Instead, growth unfolded slowly, through countless small steps, guided by gravity, motion, and time. This process is known as accretion, and it is far less dramatic than the word might suggest. At first, accretion involved dust grains no larger than grains of sand. These tiny particles drifted through the disk, moving along similar paths, carried by the shared rotation of the surrounding gas. When they met, they often stuck together, not because of forceful collisions, but because gentle contact allowed electrical forces and surface textures to bind them. Over time, these small clumps became larger ones. Pebbles turned into rocks, rocks merged into boulders, boulders gathered into objects kilometers across. Each step was slow and uneven, with long periods of calm punctuated by occasional collisions. Nothing about this process required speed or violence. In fact, gentle interactions were far more effective than destructive ones. As these growing bodies moved through the disk, they swept up material that was already in motion. This is the key to how planets inherit spin. Every piece of material in the disk was orbiting the sun in the same general direction. Each grain of dust carried not only mass, but also motion. When that grain became part of a larger object, its motion did not disappear. It added to the motion of the growing body. One grain made almost no difference. Millions did. As accretion continued, the combined effect of all this incoming material built up into a clear sense of rotation. The growing planet did not need to be spun like a top. It accumulated spin naturally, simply by collecting matter that was already moving. This process favors consistency. Material approaching a growing planet from the disk tends to arrive along paths shaped by the disk's rotation. Collisions that add spin in the dominant direction are more common than those that cancel it out. Over time, contributions in the same direction reinforce one another, while opposing motions tend to average away. The result is a planet that rotates in harmony with its surroundings. It's important to distinguish here between two related but separate motions. Orbit describes a planet's movement around the sun. Rotation describes a planet spinning around its own axis. Both motions emerge from the same rotating disk, but they are not the same thing. A planet can orbit without rotating, at least in principle. It can also rotate without orbiting another object. In the solar system, however, both motions share a common origin and often a common direction. The disk set the rules for orbit first. As material circled the young sun, it naturally settled into stable paths around it. Growing planets followed those paths, becoming locked into orbits defined by the disk's plane and direction. Orbit is therefore a large-scale motion, involving the entire planet travelling through space. Rotation is more intimate. Rotation concerns how the planet turns around its own centre. This motion develops as the planet gathers material from different directions, each contribution adding a small twist. Over time, these twists combine into a steady spin. Although orbit and rotation are distinct, they are closely linked by history. Because the same disk shapes both, they often align. Most planets orbit the Sun in one direction and rotate in that same general sense. This alignment is not guaranteed by any single rule, but it is strongly encouraged by the way accretion unfolds. As planets grow larger, their gravity becomes stronger. They begin to dominate their local regions of the disk, pulling in material from a wider area. This material still carries the disk's motion, and its arrival continues to reinforce the planet's spin. Once a planet reaches a certain size, its rotation becomes increasingly stable. Small impacts can nudge it slightly. They can speed it up, slow it down, or tilt its axis, but reversing its spin entirely becomes difficult. The accumulated motion from millions of smaller contributions has momentum of its own. Changing direction now requires something dramatic. This explains why the basic direction of rotation tends to survive the planet's formation. It also helps explain why rotation rates vary so widely. Different planets grew in different environments. Some formed quickly, sweeping up material efficiently. Others grew more slowly, interacting with gas for longer periods. Some experienced major impacts that altered their spin, while others avoided such disruptions. These differences affect how fast a planet rotates, but they do not usually erase the inherited direction. Rotation speed is flexible. Rotation direction is resilient. The surrounding gas also played a role during these early stages. Gas flowing past a growing planet could apply gentle torques, subtly adjusting its spin. Over long periods, these interactions smoothed rotation rather than randomizing it. The gas acted like a soft, persistent influence, encouraging alignment rather than disorder. As the disk evolved, gas gradually thinned and dispersed. Once it was gone, the planets were left largely on their own, carrying the spins they had acquired. From that point onward, only major events could significantly alter their rotation. This is why the imprint of early motion remains visible billions of years later. Planets today are not actively inheriting spin from a disk. They are preserving the result of a process that ended long ago. Their rotations are fossils of formation, records written in motion rather than stone. The difference between orbit and rotation becomes clearer when considering exceptions. Venus orbits the Sun in the same direction as Earth and Mars, but it rotates in the opposite sense. This tells a specific story. Venus likely formed within the same rotating disk, acquiring an initial spin aligned with the rest of the system. Later events, perhaps involving intense tidal interactions or massive impacts, altered how that inherited motion was expressed. The orbit remained stable, the rotation changed. Uranus provides another example. Its orbit fits comfortably within the solar system's shared plane, but its rotation axis is dramatically tilted. The planet still spins, still carries the imprint of formation, but its orientation was reshaped by later events. These cases underline an important point. Orbit reflects the large-scale structure of the system. Rotation reflects the detailed history of growth and interaction. Both are rooted in the same origin, but they respond differently to change. For most planets, the early conditions were gentle enough that inheritance remained clear. Accretion built worlds slowly, spin accumulated steadily, direction was preserved. In this way, planetary rotation is not a choice made by the planet. It is not a preference or a rule imposed from outside. It is a natural outcome of growing within a shared rotating environment. Each planet carries that environment within it, long after the disk itself has vanished. The slow gathering of dust and rock did more than build mass. It gathered motion, piece by piece, until entire worlds were quietly set turning. And once that turning began, it tended to stay. The early solar system was not calm. After the disk formed and planets began to grow, space near the young sun became crowded and restless. Countless rocky bodies shared overlapping paths. Some were no larger than mountains, others the size of small moons. Their orbits shifted slowly under gravity, sometimes crossing, sometimes drifting apart, rarely staying perfectly stable for long. Collisions were common, some were gentle, little more than soft mergers that added mass and motion to a growing world. Others were violent, releasing enormous amounts of energy and reshaping surfaces completely. Craters formed, mantles melted, entire chunks of material were blasted back into space. From a distance, the early solar system would have looked chaotic and unsettled. It is tempting to imagine that such violence would erase any sense of order. With so many impacts, so much instability, and so many chances for disruption, it seems reasonable to expect planetary rotation to end up random. Worlds could have been spun in any direction, their early inheritance scrambled by chance encounters, and yet that is not what happened. Despite this turbulent history, most planets retain the same general direction of rotation they acquired during formation. Speeds changed, axes tilted, surfaces were transformed, but the dominant sense of spin survived. This outcome is not accidental. It reflects how motion behaves when many events are layered on top of one another over long periods of time. To reverse a planet's rotation entirely is surprisingly difficult. A single impact must meet very specific conditions to do so. It must be large enough to deliver enormous rotational energy. It must strike at just the right angle, and it must do so without being countered by the accumulated motion already present in the planet. These requirements make complete reversals rare. Most collisions simply add to what is already there. An impact arriving in the same general direction as the planet's spin will speed it up slightly. One arriving at a different angle may tilt the axis or redistribute rotation, but it is unlikely to cancel the existing motion completely. Over time, these effects tend to average out rather than overturn the system. This averaging is crucial. In a crowded environment, impacts come from many directions. Some add spin, some subtract it. But because the planet already has a preferred direction, additions in that direction tend to be more effective. Opposing contributions often partially cancel one another before they can dominate. The existing spin acts like a stabilizing influence, making it harder for random events to fully disrupt it. The larger a planet becomes, the more resistant it is to change. As mass increases, so does the amount of rotational motion that must be overcome to alter the planet's spin significantly. Small bodies can be flipped or spun easily. Large planets require extraordinary events to experience comparable changes. By the time planets reach substantial size, their inherited rotation was already well protected. This helps explain why early chaos did not win. The solar system experienced instability, but it was not endless. Over time, collisions reduced the number of roaming bodies. Orbits became more spaced out. Resonances formed. Gravitational interactions smoothed the system into a more stable configuration. As chaos diminished, the opportunity for major spin-altering impacts decreased as well. What remained were planets carrying the cumulative result of their early history. Some worlds bear clear scars of this turbulent era. The Moon likely formed from a massive collision involving the early Earth. Mercury's oversized core suggests violent stripping of its outer layers. Uranus's extreme tilt points to a dramatic encounter long ago. These events mattered deeply, but even in these cases the underlying pattern remains. Earth's rotation direction survived the moon-forming impact. Uranus still spins in the same general sense as the rest of the system, despite its unusual orientation. Mercury rotates slowly, but it did not reverse its inherited direction. The chaos altered details, not the foundation. This resilience comes from how motion accumulates over time. Planetary rotation is not the result of one decisive moment. It is built gradually through millions of small contributions. Each impact adds a little. Each accreted fragment leaves a trace. By the time major collisions occur, they are acting on a system with a long history of motion already embedded within it. Overturning that history requires more than noise. It requires a clear, dominant counterforce. Such events are possible, but uncommon. Venus stands as a reminder that chaos can sometimes leave a dramatic mark. Its slow, reversed rotation suggests a past shaped by extreme interactions, possibly involving intense tidal forces or multiple large impacts. But Venus is notable precisely because it is unusual. Its behavior draws attention because it departs from the pattern seen elsewhere. Most planets did not experience such a fate. Instead, their early chaos acted more like a sculptor than a destroyer. It reshaped surfaces, altered compositions and refined structures, while leaving the deeper motion largely intact. The dominant spin direction, inherited from the disk, proved surprisingly robust. There was also a timescale element at work. The most violent period of planetary formation did not last forever. Once the largest bodies formed and cleared their surroundings, the system settled. With fewer potential impactors, opportunities for dramatic rotational changes dwindled. What remained was a calmer environment in which existing spins could persist with little interference. From that point onward, evolution slowed. Tidal interactions between planets and moons gradually adjusted rotation rates. Stellar radiation influenced atmospheres. Internal processes shaped geology. But these effects acted gently, over billions of years, modifying spin rather than overturning it. The result is a solar system that still carries the imprint of its earliest motion. The fact that chaos did not erase this imprint is not a sign that the early system was peaceful. It was not. Instead, it shows that order can emerge from disorder when underlying patterns are strong enough. The rotating disk provided such a pattern. It established a shared direction early on, and that direction acted as a baseline against which later events played out. Chaos added complexity, but it did not rewrite the entire script. In this way, planetary rotation tells a story of balance. Violence occurred, but it was bounded. Randomness existed, but it was constrained. The dominant motion, once established, proved difficult to overthrow. What survived was not perfection, but coherence. The early solar system was chaotic, but it was not forgetful. Its planets remember how they began to turn, even after everything else around them changed. Planets are not the only objects that carry the memory of motion. Their moons do as well. Across the solar system, moons repeat the same pattern seen at larger scales. They orbit their planets in preferred planes. Many move in the same general direction as their parent world's rotation. Some even rotate in ways that echo the history of their formation. These smaller bodies act like quieter versions of planets, preserving the same physical principles in miniature. Moons form in several different ways, but none of them are truly random. One common pathway involves disks, just as with planets. When a large planet forms inside the protoplanetary disk around the Sun, it can gather its own smaller disk of gas and debris. This circumplanetary disk behaves like a scaled-down version of the original solar disk. It flattens, rotates, and gradually feeds material into orbit around the growing planet. Within that disk, moons can form through accretion. Dust grains collide and stick. Small clumps grow into larger ones. Over time, these objects sweep up material along shared orbital paths, eventually becoming stable moons. Because the disk itself rotates in the same direction as the planet, the moons that form within it naturally inherit that motion. This is why many moons orbit in the same direction as their planet's rotation. Jupiter's large moons provide a clear example. Io, Europa, Ganymede, and Callisto all orbit close to Jupiter's equatorial plane and move in the same general direction as the planet's spin. Saturn's major moons follow a similar pattern, tracing smooth, orderly paths that reflect the structure of the disk in which they formed. This arrangement is not accidental. It is the expected outcome of formation within a rotating environment. But not all moons form this way. Some moons are captured objects, bodies that formed elsewhere and were later pulled into orbit around a planet. These moons often follow more irregular paths. Their orbits can be tilted, elongated, or even reversed. They stand out precisely because they do not share the orderly patterns of disk-formed moons. This contrast reinforces the importance of origin. When moons form alongside their planet, within a rotating disk, they tend to move together in predictable ways. When they arrive later from elsewhere, their motion reflects a different history. Even so, once captured, moons do not escape the influence of gravity and time. Over long periods, interactions between a planet and its moons can reshape motion in subtle but powerful ways. Tidal forces stretch and squeeze moons as they orbit, converting orbital energy into heat. These same forces can gradually alter rotation, locking moons into stable configurations. This is why many moons always show the same face to their planet. Earth's moon is a familiar example. It rotates at exactly the same rate that it orbits Earth, resulting in one hemisphere permanently facing its parent world. This state is known as tidal locking, and it is a natural outcome of long-term gravitational interaction. No decision is involved. No mechanism needs to be switched on. Given enough time, tides gently guide the system toward this arrangement. Many other moons behave the same way. Jupiter's large moons are tidally locked. Saturn's moons are as well. Even small moons around distant planets often settle into similar states. Rotation and orbit become synchronized, further reinforcing the idea that motion remembers its past but continues to evolve within clear boundaries. These processes mirror what happens at larger scales. Just as planets inherit rotation from disks and later have that rotation modified by impacts and tides, moons inherit motion from their local environments and then gradually adjust. The details differ, but the underlying logic remains the same. Rotation is passed down, direction tends to persist. Change happens slowly unless something dramatic intervenes. The repetition across scales is striking. A cloud collapses and spins, a disk forms and flattens. Planets grow and rotate. Moons gather and orbit. At each step, the same physical principles apply. Gravity pulls inward, motion resists collapse, rotation emerges and is preserved. The universe does not reinvent its rules for small systems, it reuses them. Even ring systems reflect this pattern. Saturn's rings orbit in a thin plane aligned with the planet's equator. They move in the same direction as Saturn's rotation. Although they are made of countless individual particles rather than solid moons, their behavior follows the same logic. They're shaped by rotation, flattened by collisions and ordered by gravity. In this sense, moons and rings are not separate curiosities. They are part of a continuum. Small disks around planets resemble larger disks around stars. Moons resemble small planets. The physics scales smoothly, with complexity increasing but principles remaining familiar. There is also an important lesson here about stability. Systems that share motion tend to be long-lived. Moons that orbit in the same direction as their planet's rotation are generally more stable than those that move against it. Their interactions are gentler. Their orbits evolve more predictably. Over time, this favors the survival of aligned systems. Misaligned moons can persist, but they often tell stories of capture, disturbance, or recent change. They're reminders that not everything forms neatly, but also that neatness has advantages. The same is true for planets themselves. Shared rotation is not just a historical artifact. It contributes to long-term stability. It reduces chaos. It allows systems to settle and endure. From moons to planets to stars, alignment is not required, but it is rewarded. This makes moons particularly valuable storytellers. They preserve details about their planet's past that might otherwise be lost. Their orbits reveal whether a disk once existed. Their rotation states hint at how long they have been interacting with their parent world. Their inclinations and eccentricities point to ancient disruptions or quiet evolution. In watching moons, astronomers see echoes of the same processes that shape the planets. Each moon is a small record of motion, written in orbit and spin rather than rock. Together they form a layered history, showing how the same basic ideas repeat across size and scale. The solar system is not a collection of unrelated objects. It is a hierarchy of rotating systems nested within one another, disks within disks, orbits within orbits, motion inherited, reshaped but rarely forgotten. Moons may be smaller and quieter than planets, but they carry the same memory. They turn, they circle, and they settle into patterns that reflect how they came to be. In doing so, they remind us that the rules governing spinning worlds are not reserved for the grandest objects. They apply everywhere. Among all the planets in the solar system, Venus stands apart. It orbits the Sun in the same direction as Earth, Mars, and the rest of the planetary family. Its path around the Sun fits neatly within the shared plane of the solar system. In many ways, Venus looks like it should behave just like its neighbours. But when it comes to rotation, Venus does something unexpected. Viewed from the same reference frame used for the other planets, Venus rotates in the opposite direction. While most planets spin anti-clockwise, Venus turns clockwise. It also does so extremely slowly. One full rotation of Venus takes longer than a full orbit around the Sun. A day on Venus is longer than a year. This combination makes Venus feel like a rebel, a planet that refused to follow the rules. It is often described as rotating backwards, or spinning the wrong way, as though it made a deliberate choice to be different. But this framing can be misleading. Venus did not decide to defy the system. Its unusual behavior reflects a long and complex history rather than a fundamental break from the processes that shaped the rest of the solar system. To understand Venus, it helps to begin where it likely started. Venus almost certainly formed within the same rotating disk as Earth and Mars. It accreted material that was moving in the shared direction of the disk. Early in its history, Venus would have inherited a rotation aligned with that environment, much like its neighbours. There is no strong reason to believe it began its life spinning the opposite way. Something changed later. The challenge is that Venus hides its past exceptionally well. Its surface is wrapped in thick clouds, and its geology appears to have been resurfaced relatively recently on cosmic timescales. Many older features that might record ancient events have been erased. As a result, scientists must piece together Venus's rotational history indirectly, using models, simulations, and comparisons rather than clear physical evidence. Several leading ideas attempt to explain how Venus ended up rotating as it does. One possibility involves massive impacts early in the planet's history. During the chaotic phase of planetary formation, large collisions were not uncommon. A sufficiently energetic impact, arriving at just the right angle, could have dramatically altered Venus's rotation. Rather than simply slowing it down or tilting its axis, such an event might have reversed the planet's spin altogether. This scenario is possible, but it comes with challenges. To reverse a planet's rotation through impact requires a very specific set of conditions. The impactor must be large, the collision must be well aimed, and the timing must be just right. While not impossible, such events are rare, which may help explain why Venus is an exception rather than the norm. Another idea focuses on Venus's atmosphere. Venus has an extraordinarily thick atmosphere, far denser than Earth's. This massive envelope of gas is constantly moving, driven by intense heat and powerful winds. Over long periods of time, interactions between the atmosphere and the solid planet beneath it could apply steady torques that alter rotation. In this view, Venus's spin was gradually slowed and possibly reversed by atmospheric tides. The Sun's gravity raises tides not only in oceans but also in atmospheres. On Venus, these atmospheric tides are particularly strong. As the atmosphere heats and cools, it can exchange angular momentum with the planet itself. Over billions of years, this slow, persistent interaction could have reshaped Venus's rotation without requiring a single dramatic event. There is also the influence of tidal forces from the Sun. Venus orbits relatively close to the Sun, and tidal interactions between the two bodies are significant. These tides act to modify rotation, often slowing it down. In combination with atmospheric effects, solar tides may have played a role in pushing Venus toward its current slow, reversed state. None of these explanations stands alone as a complete answer. The most likely explanation is a combination of factors. Early impacts may have altered Venus's initial spin. Atmospheric tides may have continued to modify it. Solar tides may have helped lock the planet into its present configuration. Over immense spans of time, these influences could work together to produce the outcome observed today. What matters is that none of these processes violate the underlying principles that shape the rest of the solar system. Venus did not ignore angular momentum. It did not escape the influence of the rotating disk. Its rotation was not random. Instead, its history involved extreme interactions that reshaped how inherited motion was expressed. In this sense, Venus does not break the rule. The rule is not that every planet must rotate anti-clockwise forever. The rule is that planets inherit rotation from their formation environment, and that rotation is then modified by later events. Most planets experienced relatively gentle histories that preserved their original direction. Venus experienced a more disruptive one. Its unusual spin is evidence of how resilient rotation usually is, and how exceptional the circumstances must be to change it so dramatically. There is also an important reminder here about perspective. Calling Venus's rotation backwards assumes that anti-clockwise is the correct direction. But as discussed earlier, direction depends on viewpoint. Venus's rotation is different relative to the rest of the solar system, not wrong in any absolute sense. The key point is that it stands out because it diverges from a shared pattern, not because it violates a universal rule. Venus's slow rotation also adds another layer to the story. A slow spin suggests that energy has been lost over time, likely through tidal interactions. The planet did not simply flip direction and continue spinning rapidly. Its motion was gradually damped, reshaped, and settled into a stable configuration. This kind of evolution takes patience, not violence alone. Venus in this way tells a story of cost. To be different required extraordinary circumstances. It required powerful interaction sustained over long periods. It required a history that most other planets avoided. The result is a world that looks familiar in size and composition, yet behaves very differently in motion. This contrast makes Venus especially valuable. By studying what makes Venus unusual, scientists gain insight into why the rest of the solar system is so consistent. Venus highlights the strength of the underlying pattern by showing how difficult it is to escape it. Exceptions, when they occur, illuminate the rule rather than undermine it. Venus also serves as a reminder that planetary histories are not identical. Shared origins do not guarantee identical outcomes. Small differences early on can be amplified over time. A slightly different impact history, a thicker atmosphere, a closer orbit to the Sun can all steer a planet onto a different evolutionary path. Yet even here, the fingerprints of formation remain. Venus still orbits within the same plane as the other planets. It still follows the same path around the Sun. Its story begins in the same rotating disk, even if it took a more complicated route afterward. In the end, Venus is not a failure of the solar system's order. It is a demonstration of how robust that order is and how much effort it takes to bend it. Uranus is often described as the oddest planet in the solar system, and at first glance that description seems well earned. Unlike the other planets, Uranus does not spin upright. Its axis is tilted by more than 90 degrees relative to its orbit, leaving the planet effectively rolling around the Sun on its side. As it travels along its long, distant path, one pole can face the Sun continuously for decades, while the other remains in darkness. Seasons on Uranus are extreme, prolonged, and unlike anything experienced elsewhere. This dramatic posture can make Uranus feel like another exception that threatens the pattern. But it is important to separate two ideas that are often blurred together. One is rotation direction, the other is axial tilt. Uranus challenges expectations about tilt, not about the fundamental sense of spin inherited from the solar system. Uranus still rotates in the same general direction as most of the other planets when described from its own north. It did not reverse its rotation in the way Venus did. What changed was the orientation of its axis, not the direction of its spin. This distinction matters. Rotation direction describes which way a planet turns around its own axis. Axial tilt describes how that axis is oriented relative to the planet's orbit. A planet can spin in the usual direction while being tipped dramatically. Uranus is a perfect example of this separation. Understanding how such an extreme tilt could arise requires looking back to the early solar system, when planets were still growing and orbits were less settled. During that time, Uranus was not the smooth, serene world it appears to be today. It was assembling mass, interacting with nearby material, and occasionally colliding with other large bodies. The outer solar system, though less crowded than the inner regions, still experienced significant encounters. One leading idea is that Uranus suffered one or more massive impacts during this formative period. A collision involving a body several times the mass of Earth's moon could have delivered enough angular momentum to tip the planet over without completely disrupting it. Such an impact would not need to reverse Uranus's spin. It would simply need to reorient the axis around which that spin occurred. This is a subtle but powerful effect. Imagine spinning a wheel while gradually tilting its axle. The wheel continues to rotate in the same sense, but its orientation changes dramatically. Uranus likely underwent a similar transformation, with its internal rotation preserved while its axis was knocked into a new position. There are reasons to think this explanation fits well. Uranus has a system of moons that orbit in a plane aligned with its equator rather than the plane of the solar system. This suggests that whatever tilted the planet happened early enough for its moons to form afterward, within a disk aligned to the new orientation. The moons did not cause the tilt, they adapted to it. Uranus also has a magnetic field that is unusually tilted and offset relative to its rotation axis. This complexity hints at a turbulent past and an interior that was reshaped by powerful events. Other possibilities have been explored as well. Some models suggest that instead of a single catastrophic impact, Uranus may have experienced a series of smaller collisions that gradually tipped it over. Each event would have nudged the axis slightly, with the cumulative effect producing the extreme tilt observed today. Another idea involves gravitational interactions with other massive bodies in the early solar system. As planets migrated and shifted, resonances could have altered Uranus's orientation over time. These scenarios are more complex and less certain, but they illustrate an important point. Extreme outcomes do not require new physics. They emerge from the same processes that shape more ordinary worlds, given the right sequence of events. Uranus did not step outside the rules of planetary formation. It followed them into a less common configuration. Despite its unusual tilt, Uranus still fits comfortably within the broader pattern of the solar system. It orbits the Sun in the same direction as the other planets. Its orbit lies close to the shared plane defined by the solar system's formation disk. Its rotation, when described relative to its own axis, follows the same inherited sense as its neighbours. The difference lies in how that axis is oriented in space. This distinction helps explain why Uranus feels dramatic but does not undermine the story of shared spin. The solar system's pattern concerns agreement in motion, not identical postures. Uranus agrees on how to rotate, even if it does so from an unusual angle. There is also a useful lesson here about stability. Once Uranus was tilted, that orientation became stable. A spinning planet resists changes to its axis, much like it resists changes to its rotation direction. After the early chaotic period ended, there were few forces capable of significantly altering Uranus's posture. The planet settled into its sideways configuration and remained there. Its moons, rings, and magnetic field adjusted accordingly. Over time, what may have begun as a violent disruption became an enduring characteristic. Uranus's tilt stopped being an accident and became part of the planet's identity. From a broader perspective, Uranus demonstrates how the solar system balances order and variation. Shared rotation provides a foundation. Individual histories add complexity. Some planets experience gentle evolution. Others, like Uranus, took a more dramatic path. Yet all of them remain connected to the same origin. This balance is important. If the solar system were perfectly uniform, it would tell a simpler but less informative story. The presence of worlds like Uranus shows how sensitive outcomes can be to early conditions, without erasing the deeper patterns that tie everything together. Uranus also reminds us that appearances can be misleading. A planet that looks wildly different can still be governed by familiar rules. A sideways world can still carry the same inherited motion as its neighbours. Extreme tilt does not imply chaos at the deepest level. It reflects history layered on top of structure. In this way, Uranus does not stand outside the story of planetary rotation, it enriches it. By separating tilt from direction and orientation from inheritance, Uranus shows how flexible planetary outcomes can be without breaking the underlying logic of formation. The physics that shaped Earth also shaped Uranus. The difference lies not in the rules, but in the path taken through them. Uranus spins like the others. It just simply does so while lying down. When exceptions appear, it is tempting to see them as failures of a rule. A planet that spins the wrong way or lies on its side can feel like a crack in the logic of the solar system. If the system truly followed a shared pattern, why would any world behave differently at all? Why would nature allow such oddities if order were really so important? But this way of thinking misses something subtle. Exceptions are not signs that a pattern is weak. Very often they are signs that the pattern is strong enough to be tested. To understand this, it helps to be clear about what the pattern actually is. The rule of the solar system is not that every planet must rotate at the same speed, or tilt at the same angle, or look broadly similar. The rule is quieter than that. It is that planets form within a shared rotating environment, inherit motion from that environment, and then carry that motion forward unless something significant intervenes. That is the rule. Everything else is detail. When planets differ from one another, they are not rejecting this rule. They are revealing how history shapes outcomes within it. Each planet's rotation is the result of both inheritance and experience. The inheritance comes from the rotating disk. The experience comes from impacts, tides, interactions, and time. Most planets experienced relatively gentle histories. Their early environments were active but not extreme enough to erase the motion they inherited. As a result, their rotations still clearly reflect the disk from which they formed. A few planets experienced more dramatic paths. Venus and Uranus are the most obvious examples. Venus spins slowly and in the opposite direction. Uranus spins at a dramatic angle. These differences can seem startling, but they do not represent random outcomes. They are the result of specific events layered on top of an already structured system. The important point is that these events had to work hard to produce such differences. Reversing rotation, or tilting a planet by more than 90 degrees, is not easy. It requires enormous energy, precise timing, or sustained interaction over vast periods of time. The fact that such outcomes are rare tells us something important about the stability of inherited motion. If planetary rotation were fragile, exceptions would be common. Spins would scatter in every direction. Instead, they cluster tightly, with only a handful of outliers. That clustering is the signal. Consider what would be expected in a truly chaotic system. If planets formed independently, or if rotation were easily scrambled, there would be no dominant direction at all. Some planets would rotate one way, some the other, many at odd angles. There would be no reason to speak of a pattern in the first place, but that is not what is seen. Instead, the solar system shows a clear default behavior. Planets tend to orbit in the same direction. They tend to rotate in the same sense. They tend to align their moons and rings accordingly. Deviations exist, but they are layered on top of this default rather than replacing it. This is why exceptions strengthen the pattern rather than weaken it. They demonstrate how much must happen to break away from the norm. They show that order is not accidental but resilient. They reveal that the solar system is not balanced on a knife edge, but built around stable tendencies. Even Venus, often described as the ultimate rule breaker, still fits this framework. Venus almost certainly began with a rotation aligned with the rest of the system. Its current state reflects later modification, not a different origin. The disk did not fail to influence Venus. Venus simply had its inherited motion reshaped more dramatically than most. The same is true for Uranus. Its extreme tilt reflects a violent history, but its rotation direction still traces back to the same rotating disk. The axis moved. The motion did not vanish. Seen this way, exceptions become records. They preserve information about the most extreme events in planetary history. They tell scientists where collisions were largest, where tides were strongest, where atmospheres played an outsized role. They are not noise, they are data. There is also an important lesson here about how rules operate in nature. Rules in physics are rarely commands. They do not dictate exact outcomes. Instead, they describe tendencies. They tell us what will happen most of the time, under most conditions, given enough time. Planetary rotation follows this pattern. The rotating disk sets a tendency towards shared motion. Accretion reinforces it. Conservation of spin preserves it. Chaos can modify it, but usually not erase it. Only under unusual circumstances does the outcome diverge strongly from the default. This kind of rule allows for variety without losing coherence. It explains why planets can look so different while still belonging to the same family. Why some rotate quickly and others slowly. Why some tilt modestly and others dramatically. Why moons and rings show both order and individuality. The consistency lies beneath the variation. Another way to see this is to imagine removing the exceptions entirely. If Venus rotated normally and Uranus stood upright, the solar system would appear even more uniform, but it would also be harder to understand. There would be fewer clues about the role of impacts, tides, and long-term interactions. The system would look tidy but less informative. Exceptions add texture. They remind us that planetary formation is not a single moment, but a long story. They show that inheritance is only the beginning, and that evolution continues long after the disk has vanished. They also help refine the rule itself. Without exceptions, it might be tempting to think that rotation direction is fixed and immutable. Venus shows that it is not. Uranus shows that orientation can change dramatically. Together they clarify what is truly conserved and what is flexible. What is conserved is the tendency to inherit motion from formation. What is flexible is how that motion is later expressed. This distinction matters. It prevents oversimplification. It keeps explanations honest. It acknowledges complexity without abandoning structure. In this way, exceptions act as stress tests. They push the system to its limits and reveal where those limits lie. The fact that the overall pattern survives those tests is evidence of its strength. There is also something quietly reassuring about this balance. The solar system is not rigid. It allows for surprise. It tolerates disruption, but it is not forgetful. It carries its history forward, even when that history is complicated. Most planets tell a simple version of the story. A few tell a more dramatic one. Together, they show how order and individuality coexist. The rule, when stated plainly, is not fragile at all. Planets form in a rotating disk. They inherit that rotation. Later events can modify, tilt, or even reverse it, but only with effort. Everything observed fits within that framework. Once that is understood, the solar system no longer feels like a collection of contradictions. It feels like a system that remembers where it came from, even when it takes unexpected paths along the way. The exceptions do not undermine the pattern. They reveal how deeply it is embedded. Left and right feel deeply familiar. They are built into everyday life, into language, into how objects are arranged on a page or a screen. Maps have an up and a down, clocks turn a certain way, instructions assume a shared sense of orientation. These ideas feel so natural that it is easy to forget they are conventions rather than features of the universe itself. In space, left and right do not exist in the same way. There is no absolute up, no universal down, no preferred orientation written into the fabric of the cosmos. Without a reference point, direction loses its meaning. Motion still exists, but the labels applied to it are entirely dependent on perspective. This is why descriptions like anti-clockwise are always relative. When astronomers describe planetary rotation as anti-clockwise, they are not pointing to a cosmic rule about which way things should turn. They are choosing a viewpoint, agreeing on a frame of reference, and using language to describe motion within that frame. The motion is real. The label is not fundamental. This distinction matters. If the solar system were observed from the opposite side, everything described as anti-clockwise would appear clockwise instead. Orbits would reverse. Rotations would flip. Nothing physical would change. Only the words would. This can feel counterintuitive because daily experience rarely requires shifting perspective so freely. On Earth, gravity gives a clear sense of down. The horizon gives a sense of level. Maps reinforce the idea that north belongs at the top. These anchors make direction feel fixed. But remove those anchors, and direction becomes flexible. Imagine floating in deep space with no nearby stars, no planets, no reference points at all. In such an environment, left and right would be meaningless. Even spin would be hard to describe without choosing an arbitrary viewpoint. This is why physicists are careful about how they talk about motion. They focus less on labels and more on relationships. Motion relative to what? Rotation with respect to which axis? Orientation compared to which plane? These relational descriptions remain meaningful even when absolute directions disappear. The solar system is a perfect example of this approach. Its planets share a plane. They orbit in a consistent direction relative to that plane. They rotate in a consistent sense relative to their orbits. These relationships persist regardless of how the system is oriented in space. The choice to call that direction anti-clockwise is simply a convenience. It allows astronomers to communicate clearly and consistently. It provides a shared language, but it does not imply that the universe prefers anti-clockwise over clockwise, or that one direction is more correct than the other. This becomes clearer when considering other planetary systems. There is no reason to expect every solar system in the galaxy to spin the same way. Some likely rotate in the opposite sense relative to ours. From within those systems, their planets would appear to rotate anti-clockwise when viewed from their chosen north. From our perspective, they might appear reversed. Both descriptions would be valid within their respective frames. The universe does not enforce a single-handedness for planetary systems. It allows either outcome. What matters is consistency within each system, not alignment across all of space. This brings the focus back to origin. The direction a system spins is determined by the tiny initial motions present when its parent cloud began to collapse. Those motions could just as easily have gone the other way. There is no known reason they had to point in one particular direction. Once chosen, however, that direction tends to persist. The collapse amplifies it. The disk preserves it. Accretion reinforces it. Planets inherit it. The result is a system that feels orderly, not because it chose the right direction, but because it chose a direction at all. This perspective helps dissolve a common misunderstanding. When people ask why planets rotate anti-clockwise, they often imagine that anti-clockwise is the phenomenon that needs explaining. In reality, the explanation has nothing to do with clockwise or anti-clockwise specifically. It has everything to do with shared motion and inherited rotation. The meaningful question is not why that direction, but why the same direction? Why do planets agree with one another? Why does that agreement survive chaos, impacts, and time? Why is the pattern so persistent? Once framed this way, the answer becomes much clearer. The solar system is coherent because it formed together. Its planets share a common history. Their motion reflects that history more than any abstract notion of direction. This is also why exceptions are so informative. When a planet deviates from the shared pattern, it does not suggest that left and right suddenly matter. It points instead to a unique history layered on top of the same origin. The language of direction helps describe the deviation, but the cause lies in events, not labels. Even Venus, with its reversed rotation, does not care about clockwise or anti-clockwise. Its motion reflects interactions with tides, impacts, and atmosphere. The words are simply a way to describe the outcome. There is something quietly freeing in this realization. It means the universe is not biased toward one direction. It is indifferent. Order emerges not because of preference, but because of process. Systems that begin with a shared motion tend to keep it. Left and right, clockwise and anti-clockwise, are tools for human understanding. They help turn motion into language, but they are not part of the underlying machinery. What truly matters is agreement. Planets formed together tend to move together. They spin in harmony not because the universe insists on a particular direction, but because history nudges them into alignment and then refuses to let go. When the labels fall away, what remains is a simple and powerful idea. Motion remembers where it came from, and in the vastness of space, that memory matters far more than the words used to describe it. Rotation does far more than decide which way a planet turns. It shapes the lived experience of that world, setting the rhythm of light and darkness, steering winds and oceans, and quietly influencing how stable or extreme a planet becomes over time. The most immediate effect of rotation is the cycle of day and night. As a planet spins, different parts of its surface take turns facing its star. When a region turns toward the light, it warms. When it turns away, it cools. This simple alternation creates the basic pulse of a planet's environment. On Earth, this rhythm feels so familiar that it is easy to feel it is inevitable. But across the solar system, rotation rates vary enormously, and so do their consequences. Some planets spin quickly, producing short days and rapid temperature changes. Jupiter completes a rotation in less than half an Earth day, causing its atmosphere to whip around the planet at tremendous speeds. Other worlds rotate very slowly. Venus takes longer to turn once than it does to orbit the Sun, creating days and nights that stretch for months. On such a world, the Sun lingers overhead for an extraordinarily long time, allowing heat to build and linger in ways that would feel alien on Earth. These differences matter because rotation controls how energy is distributed. A fast-rotating planet spreads heat more evenly. Day and night alternate quickly, preventing extreme temperature differences between the sunlit and dark sides. A slow-rotating planet allows heat to accumulate on one side while the other cools deeply, increasing contrasts and stressing the atmosphere. Rotation also plays a central role in shaping weather. As air or gas moves across a rotating planet, it does not travel in straight lines relative to the surface. Instead, rotation causes moving air to curve, creating large-scale circulation patterns. These deflections organize winds into bands, storms, and long-lived systems that define a planet's climate. On Earth, this effect contributes to trade winds, jet streams, and the general circulation of the atmosphere. On Jupiter and Saturn, where rotation is rapid and atmospheres are deep, it produces striking bands of clouds that wrap around the planet and massive storms that can last for centuries. Without rotation, weather would look very different. Air heated by a star would rise and flow directly toward cooler regions, then sink and return, creating simple circulation patterns. Rotation complicates this flow, breaking it into smaller cells and adding structure. The result is weather that is dynamic rather than uniform. Rotation also affects oceans where they exist. On Earth, the spinning planet influences how currents move across the surface, helping distribute heat from the equator toward the poles. These currents moderate climate, making some regions warmer and others cooler than they would otherwise be. Without Earth's rotation, ocean circulation would be simpler and less effective at balancing temperatures. Spin even affects how storms behave. On a rotating planet, storms tend to organize and persist, drawing energy from temperature differences and angular motion. Hurricanes on Earth, for example, rely on rotation to maintain their structure. On a non-rotating world, such organized storms would struggle to form. Beyond weather, rotation contributes to a planet's overall shape and stability. Rapidly rotating planets tend to bulge slightly at their equators. This flattening is subtle for rocky worlds like Earth, but dramatic for gas giants like Saturn, whose equatorial diameter is noticeably larger than its polar diameter. This shape is a direct consequence of rotation, reflecting the balance between gravity pulling inward and motion pushing outward. Rotation also helps stabilize a planet's orientation. A spinning object resists changes to its axis, a property that helps keep a planet's tilt relatively steady over long periods. This stability matters for climate. A wildly changing axis would produce erratic seasons, making long-term environmental patterns difficult to sustain. While axial tilt can change slowly over time, rotation helps prevent sudden, chaotic shifts. Even a planet's internal structure can be influenced by spin. Rotation affects how material moves inside a planet, shaping patterns of convection in mantles and cores. These motions are tied to magnetic fields, which themselves play a role in shielding atmospheres from stellar winds. While many factors influence magnetic field generation, rotation is an important ingredient. In this way, spin contributes to a planet's ability to retain an atmosphere. A stable magnetic field can protect a planet's surface from energetic particles streaming from its star. Without such protection, atmospheres can be stripped away over time, as appears to have happened on Mars. While rotation alone does not guarantee a magnetic field, slow or chaotic rotation can make field generation more difficult. Rotation also interacts with a planet's distance from its star. Worlds close to their stars can become tidally locked, meaning they rotate once for each orbit, always showing the same face to the star. In these cases, day and night cease to alternate globally. One side remains in perpetual daylight, the other in constant darkness. This arrangement profoundly affects climate and habitability, concentrating heat on one hemisphere and challenging the atmosphere to redistribute it. Even here, rotation still matters. A tidally locked planet still rotates relative to its own axis, just very slowly. The way its atmosphere responds depends on how efficiently heat can be moved from the day side to the night side. Some models suggest that with the right atmospheric conditions, such planets can still maintain stable climates, though very different from Earth's. What becomes clear is that rotation is not a cosmetic feature. It shapes how a planet breathes, how it circulates energy, how it responds to its star, and how stable it remains over time. It influences nearly every surface condition, from temperature patterns to storm behavior. This is why inherited spin matters so much. The direction of rotation may be a matter of perspective, but the presence of rotation and its rate are physically meaningful. They affect the long-term evolution of a planet in ways that are difficult to undo. Even small changes in rotation rate can have large consequences. A slightly faster spin can strengthen winds. A slightly slower one can allow heat to pool. Over millions of years, these differences shape landscapes, atmospheres, and internal dynamics. Seen this way, rotation is not just a relic of formation. It is an active participant in a planet's ongoing story. The spin inherited from the disk sets initial conditions, but the planet continues to live with the consequences of that motion long after formation ends. The solar system's shared rotation direction therefore carries more weight than it first appears. It means that planets did not just form together, they developed within similar dynamical environments. Their early spins placed them on comparable footing, even as later events drove them apart in detail. Some planets became stormy giants, others cooled into rocky worlds, some lost atmospheres, others retained thick envelopes of gas. But all of them began with rotation, and that rotation helped shape the paths they followed. In this sense, spin is not merely about which way a planet turns, it is about how a world lives. Rotation sets the tempo of a planet's days, the choreography of its winds, and the stability of its climate. It connects deep interior processes to surface conditions and links formation history to present behavior. Once motion is inherited, it continues to matter. Long after the disk has vanished, long after impacts have faded, and long after surfaces have changed, rotation remains, quietly influencing everything that unfolds on a spinning world. For a long time, the solar system was the only example available. Everything known about planetary formation, rotation, and structure had to be inferred from a single system, observed from the inside. That made it tempting to wonder whether the patterns seen here were special, perhaps the result of unusual circumstances rather than universal processes. That question began to change once other stars came into view. As telescopes improved, astronomers started to look not just at stars themselves, but at the material surrounding them. What they found was strikingly familiar. Young stars, especially those still forming, were often wrapped in broad, flattened disks of gas and dust. These disks glowed faintly, warmed by starlight, their shapes revealed by subtle shadows and gentle spirals. These were protoplanetary disks. They are the birthplaces of planets, and they appear throughout the galaxy. Wherever stars are forming, disks tend to form as well. They are not rare, fragile structures. They are common, persistent, and remarkably consistent in shape. The resemblance to the early solar system is hard to miss. These disks are flat. They rotate as they surround a central star. They look exactly like what theory predicted long before they could be observed directly. The reason is simple. The same physics applies everywhere. When a cloud of gas collapses under gravity, any small amount of initial motion is amplified. Rotation increases as the cloud shrinks. Material that cannot fall straight inwards spreads into orbit. Collisions damp vertical motion, flattening the structure into a disk. None of this depends on location, composition, or cosmic era. It is a natural outcome of gravity and motion working together. Because of this, astronomers do not expect planetary systems to form in wildly different ways from one another. Details vary, but the broad structure remains the same. A rotating cloud leads to a rotating disk. A rotating disk leads to planets that share a plane and a direction of motion. Observations support this expectation. Many protoplanetary disks show signs of gaps and rings, features thought to be carved by forming planets. These planets, still embedded in their birth environments, are already shaping the disk around them. The entire system rotates together, with material flowing along curved paths defined by the disk's motion. In some systems, multiple disks are observed around stars that form together in clusters. Each disk has its own orientation, but within each system the internal agreement remains. Planets forming in the same disk share motion with one another, even if neighbouring systems spin in different directions. This is an important point. There is no universal direction that all planetary systems follow. Some disks rotate one way, others the opposite, depending on the tiny initial motions present in their parent clouds. What is universal is not the direction chosen, but the fact that a direction is chosen and preserved. Consistency appears within systems, not across the entire galaxy. This reinforces the idea that the solar system is not unusual, it is representative. The same processes that shaped Earth, Mars and Jupiter are shaping planets around other stars right now. The same balance between gravity and motion is at work. The same tendency toward flattened disks and shared rotation appears again and again. Even when planets are discovered around other stars, their arrangements often echo what is seen at home. Many exoplanets orbit within flat systems, with multiple planets tracing paths close to a common plane. In some cases, these planets appear to orbit in the same direction as the rotation of their host star, suggesting a shared formation history within a rotating disk. There are exceptions, of course. Some systems show planets on tilted or even backwards orbits relative to their star's rotation. These cases often point to later disturbances, such as gravitational interactions with other planets or nearby stars. Once again, variation appears on top of a common foundation. The pattern holds. Formation creates order. Evolution introduces complexity. What is seen elsewhere mirrors what is seen here. The universality of disks also explains why astronomers were able to predict planetary formation long before they could observe it directly. The mathematics of rotating systems applies at every scale, from spinning ice skaters to swirling galaxies. The same principles that flatten Saturn's rings flatten protoplanetary disks. In this sense, planets forming around other stars are not exotic, they are expected. What changes from system to system are the details, the mass of the star, the temperature of the disk, the amount of material available, the timing of disk dispersal. These factors influence how many planets form, how large they grow, and how close they orbit. But the underlying motion remains familiar. Disks rotate. Planets inherit that rotation. Shared direction emerges naturally. This universality has an important implication for the question of planetary spin. If the solar system's shared rotation were a fluke, it would stand out as unusual when compared to other systems. Instead, it fits neatly into a much larger pattern. Everywhere astronomers look, they see the same ingredients arranged in the same basic way. The universe does not need to invent a new method each time a star forms. It reuses what works. This repetition also helps explain why the idea of planets rotating in the same direction should not feel surprising once understood. It is not a coincidence layered on top of chaos. It is a predictable outcome of how matter behaves when allowed to collapse and rotate. The fact that this outcome appears again and again strengthens confidence in the explanation. It is not built to explain one system after the fact. It predicts behavior that is observed elsewhere. There is something quietly comforting in this consistency. It suggests that the solar system is not an isolated accident, but part of a much broader family of systems shaped by the same gentle rules. The night sky is full of stars that likely host planets turning together, sharing inherited motion, following the same basic script. Even though each system tells its own story, the opening chapter is remarkably similar. A cloud drifts, gravity gathers it, rotation emerges, a disk forms. From that point onward, shared motion becomes the default rather than the exception. This does not diminish the uniqueness of individual worlds. It places that uniqueness within a stable framework. Differences arise not because the rules change, but because the timing and interactions differ. The solar system's behavior, then, is not a curiosity to be explained away. It is an example of something much larger. Other stars forming elsewhere in the galaxy follow the same behavior because they are built from the same ingredients and governed by the same principles. The universality of disks and shared rotation is not imposed by design. It is a natural outcome of physics that operates everywhere. Once this is seen, the question of why planets rotate the same way begins to feel less mysterious. It is what rotating systems do, here, elsewhere. Everywhere stars and planets are born. Rotation does not stop at the scale of planets and stars. It extends outward, shaping structures far larger than any solar system. Galaxies spin too. At first glance, galaxies appear almost static. Their stars are so distant, their sizes so immense that motion is difficult to perceive. But over time, careful observation reveals a slow, steady rotation. Stars orbit galactic centers. Gas clouds follow curved paths. Entire spiral arms drift around a common core. This motion is not decorative, it is fundamental. Most large galaxies rotate in an organized way, with vast numbers of stars moving together in flattened disks. The Milky Way itself is one such system. From the inside, it feels like a scattered collection of stars. From afar, it would appear as a rotating disk with graceful spiral arms extending outward. The resemblance to smaller systems is striking. Just as planets orbit a star within a disk, stars orbit the center of a galaxy within a disk. The scales are vastly different, but the structure feels familiar. A central concentration of mass, a flattened, rotating system. Motion shared across enormous distances. This similarity is not a coincidence. Galaxies form through collapse just like stars and planetary systems, though on far grander scales. Early in the universe, matter was distributed unevenly. Regions slightly denser than their surroundings began to pull in more material through gravity. As these regions grew, they gathered gas, dust, and dark matter from their surroundings. And, once again, there was motion. The material falling into a forming galaxy did not arrive perfectly still. Tiny initial motions were present from the beginning, inherited from the early universe itself. As matter collapsed inward, those motions became more pronounced, just as they did in smaller systems. The forming galaxy began to rotate. As with protoplanetary clouds, rotation influenced the shape of the collapsing structure. Material that could not fall straight inward spread into orbit. Interactions damped motion perpendicular to the main plane. Over time, the galaxy flattened into a disk, with most of its stars and gas confined to a relatively thin region compared to its overall size. This process mirrors what happens during star and planet formation, but the timescales are far longer and the distances far greater. A galaxy can take billions of years to settle into its structure. Stars orbit slowly, completing a single circuit around the galactic center over hundreds of millions of years. Yet the underlying physics remains the same. Gravity pulls inward. Motion resists collapse. Rotation emerges and persists. It is important to keep these comparisons grounded. A galaxy is not simply a scaled-up solar system. The forces involved are more complex. Interactions between stars are rare. dark matter plays a major role in shaping motion. Galaxies can merge, collide, and distort one another in dramatic ways. But despite these differences, the presence of rotation and flattened structure points to a shared logic. Rotation is a natural response to collapse. This becomes especially clear when looking at different types of galaxies. Spiral galaxies like the Milky Way show clear rotational organization. Their disks rotate smoothly, with stars moving in coordinated paths. Elliptical galaxies, by contrast, tend to be less flattened and show more random stellar motions. These galaxies often form through violent mergers that disrupt ordered rotation, scattering stars into more chaotic orbits. Even here the pattern holds. Where collapse happens gently, rotation organizes structure. Where collapse is violent, rotation is disrupted. The difference lies not in the rules but in the history. In many spiral galaxies, rotation dominates. Gas clouds orbit the center, gradually forming new stars within the disk. These stars inherit the motion of the gas from which they form, continuing the cycle. Rotation becomes self-reinforcing, shaping the galaxy's long-term evolution. This is another echo of what happens in planetary systems. Planets inherit motion from disks. Stars inherit motion from galactic disks. At each level, the same principle applies. Matter collapses. Rotation emerges. Structure follows. Galactic rotation also helps explain why galaxies look the way they do. Spiral arms are not rigid structures, but regions where stars and gas bunch up temporarily as they orbit. The rotation of the disk creates patterns that appear long-lived, even though individual stars move through them. This behavior depends on shared motion across enormous scales. Without rotation, such structures would not exist. Rotation also influences how galaxies evolve over time. It helps stabilize disks against collapse. It regulates how gas flows inward toward the center. It shapes where stars form and how material is redistributed. In this way, spin acts as an organizing influence, preventing everything from simply falling straight inward. This stabilizing role is familiar. Planets resist collapse because of rotation. Disks persist because of rotation. Galaxies avoid becoming dense, featureless blobs because rotation spreads matter outward. At every scale, spin buys time. There is also a deeper connection here. The angular momentum seen in galaxies ultimately traces back to the earliest moments of the universe. Tiny irregularities in the distribution of matter, combined with gravitational interactions, seeded motion that would later be amplified through collapse. The rotation of galaxies is, in a sense, a memory carried forward from the universe's youth. This mirrors the story told by planets. Planetary rotation preserves information about the early solar system. Galactic rotation preserves information about early cosmic structure. In both cases, motion acts as a record, storing history in its direction and distribution. The fact that rotation appears across so many scales suggests that it is not an optional feature of structure formation. It is a default outcome. This does not mean that everything spins the same way. Different galaxies rotate in different directions. There is no universal alignment across the cosmos. Just as planetary systems choose a direction based on their initial conditions, galaxies do the same. What matters is internal agreement. Within a galaxy, stars share a common rotational sense. Within a planetary system, planets do the same. These agreements arise not from preference, but from shared origin and conservation of motion. Seeing this pattern repeat helps place the solar system in context. Planets rotating together are not unusual. They are part of a broader trend in how matter organizes itself under gravity. The same behavior that flattens a protoplanetary disk flattens a galaxy. The same persistence of motion that keeps a planet spinning keeps stars orbiting galactic centers. The universe is not built from separate rules at different scales. It uses the same principles again and again, allowing complexity to grow while keeping behavior understandable. By the time attention returns to planets, their shared rotation feels less like a curiosity and more like an expectation. It is what rotating systems do when allowed to collapse and evolve without constant disruption. From planets to stars to galaxies, motion remembers. It shapes structure, it preserves history, and it links the smallest spinning worlds to the largest rotating cities of stars. Chaos often feels like the natural state of the universe. Matter drifts, collides, scatters, and rearranges itself endlessly. Stars are born in turbulent clouds, planets grow through violent impacts, galaxies collide and merge. At every scale, motion appears restless and unpredictable, especially in the early stages of formation. And yet, when these systems are observed over long periods of time, something unexpected happens. Order appears, not suddenly and not perfectly, but gradually and persistently. Patterns emerge, motions align, structures stabilize. What began as a noisy, unsettled environment slowly organizes itself into something coherent. This is not because chaos disappears, but because its effects are averaged out. Averaging is one of the quiet architects of order. When many small events occur over long timescales, their individual randomness tends to cancel out. Small pushes in one direction are balanced by small pushes in another. Irregularities smooth themselves away. What remains is the dominant, persistent motion that was present from the beginning. In rotating systems, this effect is especially powerful. Early in the life of a planetary system, countless particles move in slightly different ways. Some collide, some drift, some scatter outward. But because the system already has a shared sense of rotation, contributions aligned with that rotation tend to reinforce one another. Contributions that oppose it tend to cancel out over time. The result is not perfection, but stability. This is why shared motion persists even in the presence of chaos. Collisions do not happen in isolation. They happen within a context. That context includes the overall rotation of the system, the dominant plane of motion, and the accumulated history of spin. Individual events add noise, but the background signal remains strong. Over time, the signal wins. This is not unique to planetary systems. In galaxies, stars move on complex paths influenced by gravity, encounters, and internal dynamics. Yet despite this complexity, galaxies often maintain coherent rotation for billions of years. The details change, but the overall motion remains. The same is true in weather systems. Air molecules move chaotically, colliding constantly. But on a rotating planet, large-scale wind patterns emerge. Jet streams persist. Trade winds repeat. The chaos of individual particles averages into organized flow. Order emerges not because chaos stops, but because it is constrained. Constraints matter. Gravity provides a central pull. Rotation provides a directional bias. Conservation of motion limits how easily established patterns can be erased. Together, these constraints shape what chaos can and cannot do. Chaos is free to act, but not free to dominate. In the early solar system, this balance played out over millions of years. Impacts reshaped planets. Orbits shifted. Material was exchanged and redistributed. But each event took place within a system that already had a preferred plane and a shared direction of motion. That shared motion acted like a memory. It did not dictate every outcome, but it influenced them. It made some configurations more likely than others. Over time, this influence accumulated, nudging the system toward coherence rather than dispersion. This is why order feels inevitable in hindsight. Once the dominant patterns are established, they become self-reinforcing. Objects moving with the prevailing flow experience fewer disruptive interactions. Objects moving against it tend to collide more often, losing energy and being drawn back into alignment. Stability becomes easier to maintain than instability. This does not mean that systems become static. Planets continue to evolve. Axes tilt slowly. Orbits shift gradually. Moons migrate. Galaxies warp and ripple. But these changes unfold within a stable framework, guided by the same underlying principles that created the structure in the first place. There is also an important role played by time. Given enough time, unstable configurations tend to disappear. Orbits that cross too often lead to collisions. Motions that are wildly misaligned tend to be damped. What survives is not what was most dramatic, but what was most stable. This filtering effect quietly shapes systems. It removes extremes. It favors alignment. It rewards coherence. What remains looks orderly, not because chaos never occurred, but because chaos was allowed to play itself out. This perspective helps explain why shared planetary rotation does not require constant maintenance. Once established, it does not need to be enforced. It persists because alternatives are less stable. A planet rotating against the dominant motion is not forbidden, but it is less likely to survive unchanged. Over time, interactions tend to push systems toward agreement. Venus and Uranus stand out precisely because they represent rare paths through this filtering process. Their histories included extreme events that pushed them into unusual states. Most planets did not experience such disruptions, and so they retained the more stable outcome. The pattern is statistical rather than absolute. Nature does not guarantee identical results. It produces tendencies. Given many opportunities, those tendencies become visible as structure. Shared rotation is one such tendency, emerging naturally from the interplay of gravity, motion, and time. There is a calm elegance to this process. Nothing needs to be coordinated. No external planner arranges the outcome. The system organizes itself through simple rules applied repeatedly. Chaos supplies variation. Constraints shape it. Time selects what lasts. This balance is one of the reasons the universe feels understandable. Despite its vastness and complexity, the same principles apply again and again. The same logic that shapes a spinning disk around a young star shapes a rotating galaxy. The same averaging that smooths planetary motion smooths stellar orbits. Order emerges because it is easier to maintain than disorder. This does not make the universe rigid or dull. It makes it expressive. Variation still exists. Individual histories still matter. But they unfold within a landscape shaped by stability. From this viewpoint, shared planetary rotation feels less like a mystery and more like a natural outcome. Planets rotate together because they formed together. They keep rotating together because doing so is stable. They only diverge when something extraordinary intervenes. The pattern does not require perfection. It only requires persistence. When chaos is allowed to act within boundaries, it becomes creative rather than destructive. It explores possibilities, tests limits, and then settles into forms that can endure. That is how order emerges, not by eliminating chaos, but by letting it average out, soften, and gradually give way to patterns that last. By the time attention returns to the planets themselves, rotation no longer feels like a detail. It feels like a record. Every spinning world carries with it a quiet history, written not in rock layers or craters alone, but in motion. The way a planet turns, how fast it spins, and how its axis is oriented, all preserve information about where it came from and what it experienced along the way. Rotation is memory made physical. Long before planets existed, before the sun ignited, before orbits settled into place, there was already motion. A drifting cloud of gas carried a faint, uneven swirl. That swirl was small, almost insignificant at first, but it mattered. As gravity gathered the cloud inward, that early motion was amplified, not erased. Collapse made it clearer. Rotation made it persistent. From that moment on, the system began remembering. The disk that formed around the young sun did not choose a direction with intent. It simply inherited one. That direction shaped how material moved, how collisions unfolded, and how growing worlds gathered mass. Each planet formed within that moving environment, collecting not just matter, but momentum. Spin accumulated quietly, grain by grain, impact by impact. By the time the planets emerged as distinct worlds, their rotations were already telling a story. They told of a shared origin. They told of a common disk. They told of motion preserved rather than invented. Even when later events complicated that story, the early chapters were not erased. Impacts reshaped surfaces. Tides slowed rotations. Axes tilted. Atmospheres grew thick or thinned away. Moons formed, migrated, and locked into place. Through all of this, rotation adapted, but it did not forget. Venus tells a story of extremes. Uranus tells a story of disruption. Mercury tells a story of slowing and resonance. Each planet's spin records not just how it formed, but what happened afterward. The differences are not contradictions. They are annotations. What makes this record so powerful is that it does not need interpretation to exist. Rotation persists whether it is studied or not. Long after the disk vanished, long after the chaos of formation subsided, the planets continued turning. Their motion carried information forward through billions of years. This is why rotation is such a reliable guide to the past. Rock can be resurfaced. Atmospheres can escape. Craters can be buried. But motion is harder to erase. It can be altered, redirected, or slowed, but it rarely disappears completely. In space, where friction is scarce and time is abundant, motion becomes one of the most enduring traces of history. The shared direction of planetary rotation is therefore not a coincidence frozen in place. It is a living remnant of formation, still unfolding in real time. Even now, planets continue to spin, carrying forward the consequences of choices they never consciously made. The direction was set early. The pace evolved later. The memory remains. This way of thinking also reframes the original question. Why do almost all planets rotate the same way is not really a question about direction at all. It is a question about inheritance, about why systems formed together tend to move together, about how early conditions can echo across immense spans of time. When seen this way, the answer becomes less mysterious and more reflective. Planets rotate together because they were born together. They keep rotating together because motion is conserved. They only diverge when history intervenes forcefully enough to matter. The universe did not need to enforce this outcome. It simply allowed motion to persist. There is something quietly reassuring about this idea. It suggests that the universe is not constantly resetting itself. It carries its past forward. Small beginnings can leave lasting marks. Gentle processes, given enough time, can shape vast structures without noise or urgency. Rotation shows this better than almost anything else. From moons orbiting planets, to planets orbiting stars, to stars orbiting galactic centers, the same logic repeats. Collapse gathers matter, motion resists collapse. Disks form, rotation persists. At every scale, systems remember how they began. This repetition does not make the universe dull, it makes it legible. Patterns emerge not because outcomes are forced, but because certain behaviors are stable. Shared motion lasts because it is easier to maintain than to destroy. Order survives not because chaos is absent, but because chaos is filtered by time. The solar system, viewed through this lens, becomes less like a collection of accidents, and more like a long conversation between gravity and motion. Gravity pulls inward, motion pushes sideways, time listens patiently. What remains is structure. The planets do not spin because they must. They spin because once they began, nothing ever truly asked them to stop. Their rotation is not an obligation, it is a consequence, and consequences in physics tend to linger. As this journey slows, it is worth returning to the simplicity at the heart of it all. A cloud collapsed. It carried motion. That motion was preserved. Everything else followed. Planets formed. They spun. They changed. They endured. Their rotations still trace circles in space, quietly marking the passage of time, quietly remembering a beginning that no longer exists in any other form. In watching them turn, there is no need to imagine intention or design. There is only continuity. Motion, once started, prefers to keep going, and in that steady turning the solar system keeps telling its story, not loudly, not urgently, but with the calm persistence of something that remembers where it came from and has never felt the need to forget. When the question is asked plainly, it sounds almost whimsical. Why do almost all planets rotate the same way? It is the kind of observation that hides in plain sight, easy to overlook until someone points it out. Once noticed, it can feel as though it demands a dramatic explanation, something exotic or mysterious, something unique to our corner of the universe. But the answer turns out to be calm. Planets rotate the same way because they were born the same way. They form together, from the same drifting cloud of gas and dust inside the same rotating disk. Long before there were worlds with names, there was already motion. That motion was faint at first, barely more than a tendency, but gravity amplified it as the cloud collapsed. Rotation emerged naturally, not as a rule imposed from outside, but as a consequence of shrinking while moving. The disk that formed carried that rotation forward. Material within it shared a direction, shared a plane, shared a history. As planets grew, they gathered not only matter, but motion. Each world inherited the same quiet spin, shaped by the same early conditions. That shared rotation is not fragile. It survived impacts, chaos, and time. It was adjusted, tilted, slowed, and in rare cases reversed, but it was never erased casually. The fact that most planets still turn together billions of years later speaks to how persistent motion can be once it is established. Even the exceptions fit the story. Worlds like Venus and Uranus remind us that history matters. Their unusual rotations are not failures of the system, but records of extraordinary events layered on top of a shared origin. They show how much effort it takes to bend a pattern that is otherwise remarkably stable. When direction is set aside, what remains is agreement. Clockwise and anti-clockwise are human descriptions chosen for convenience. Space itself has no preferred left or right. What matters is that the planets agree with one another, that they move as parts of the same system, rather than as unrelated objects. This agreement is not unique to the solar system. Around other stars, disks form and rotate. Planets emerge within them, sharing motion in the same quiet way. On larger scales, galaxies flatten and spin, carrying the memory of their own formation across billions of years. Again and again, gravity gathers matter, motion resists collapse, and rotation persists. The universe does not rush these processes. It allows time to smooth chaos, to average away randomness, and to preserve what is stable. Order emerges not through force, but through patience. Patterns form not because they are required, but because they endure. Seen this way, the spinning of planets becomes something gentle rather than surprising. It is the universe remembering itself. From a drifting cloud to a glowing star, from dust grains to full worlds, the same motion carries on, quiet and uninterrupted. Each rotation is a small echo of a beginning long past, still turning, still telling the same story. In that steady movement there is no urgency, no drama, just the calm logic of the spinning system, continuing to turn simply because it always has.